Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my live streamed mathematics videos, and in particular I'm going to talk about how we can estimate errors in some of our calculations using calculus. Now the idea uses a tangent plane, and I'm going to discuss an example involving the measurement of the dimensions of a cylinder. What knock-on effect will errors in our measurements have? Okay, so let me share my screen with you and we can have a look. Okay, here's the example that we're going to walk through. We measure the dimensions of a cylinder with each measurement having an error of 1%. Obtain an estimate on the maximum percentage error in the calculated volume. Okay, so let's just draw a little picture here. You've got some sort of cylinder. Okay, it's a badly drawn cylinder, and the dimensions we want to calculate the volume are the radius of the base and the height. Now, our two measurements our R and our H, well, imagine R and H are the true measurements, the true values here, and our measurements are within 1% of those. Okay, so let's just write down what this really means. We have the following. So let say H naught be the computed value and delta H be the difference between a computed value and the real height, and the same with R. So R naught is our measured value and delta R takes care of the error in our measurement. All right, now what does this say? We say each measurement has an error of 1%. Well, that says the following. It says that delta H, the error in our measurement for the height, is plus or minus 0.01 H naught. It could be an overestimate of 1% or an underestimate of 1%, so plus and minus. Okay, so the same thing for delta R. There's an error in the measurement of 1%. Okay, so what that means is the absolute value here will be equal to take absolute values, you can get rid of the plus minus. H naught will be positive. Okay, now that'll keep us going for a little while. What we're going to do now is use an inequality, and the inequality essentially is based on the idea of a tangent plane approximation. So let me share my screen with you and show you what that means. Okay, so all right, here it is. If delta V is the error in the computed value of V, so delta V is like the volume with these true dimensions minus the value at our measured R naught and H naught, then this is less than or equal to the following. Okay, it's this derivative evaluated at this times delta H absolute plus, so by the subscripts I mean derivatives, of course, so dV dH, dV dr Okay, so this is just basically based on a tangent plane approximation. Okay, so we've got this expression here. What we're going to do is compute the partial derivatives that appear here and evaluate them at h naught and r naught. Okay, so and then multiply through by these. Now we don't know what h naught and r naught are, but that's not going to be a big problem here. Okay, so let's this v sub h. If I differentiate this with respect to h partially, I'm just going to get pi r squared. And this partial derivative here, v sub r dv dr, is going to be, so I differentiate this partially with respect to r, so differentiate with respect to r and imagine h is constant. It's going to be 2 pi rh. So using this, we can then write down the following. Okay, now with these guys, I can replace them with this, and then it's just going to be a matter of cleaning up. So this first derivative is going to be dv dh. So it's pi r squared evaluated at h naught r naught. So I'll replace r with r naught. Okay, I can replace this with 0.01 h naught. Okay, I don't really need the absolute values here. And this is going to be, okay, dv dr. So I'm going to get 2 pi rh there, and I replace that with h naught r naught. Again, times this, which is 0.01 r naught. Okay, and now I can clean. So this is 0.01 here, this is 0.01 here. I can clean this up. I don't need any absolute value signs here because everything's positive or non-negative. So what I can do, I've got a common factor of 0.01 there, and I'm going to get 2 lots of that there. So if I combine everything here, I'm going to get a h naught r naught squared and a h naught r naught squared. So I'm actually going to get the following. Okay. So remember, what we're chasing here is an estimate on the maximum percentage error in V. Okay, so I've got an estimate for the error delta V. We want to express this as a percentage error now. Okay, now over here, what is this? This is V the volume at h naught r naught, whatever those things are. So what I can do is I know this is less than or equal to this. I can take this over to the other side, put it down there, and then multiply the whole thing by 100 to get the an estimate on the maximum percentage error. So let's do that. Delta V over this, right, times 100 to give us a percentage is less than or equal to 0.03 times 100, which is just 3%. Okay, so an estimate for the maximum percentage error in our computed volume is 3%. All right, so let's write that down. The maximum percentage error in V is 3%. Okay, so that is one of those error estimation type problems. Okay, let's just run through it again very quickly. because there is a pattern there. We measured the dimensions of a cylinder, with each measurement having an error of 1%. Okay, we don't actually know what our measurements are, but we know that they have an error of 1%. Obtain an estimate on the maximum percentage error in the calculated volume. So we know that the absolute value in the error in the height measurement is 0.01 of our height measurement, and the same with the error in the radius measurement. Using this inequality here, which follows from a tangent plane approximation, we can compute this derivative, We have expressions for these things in terms of H0 and R0. We computed those things and put them in, and then we rearranged to get the V over here. The other option you could do is just divide both sides by V straight away, and this will disappear. Okay, that's another option. All right, then we rearranged and we multiplied by 100 to get our an estimate on our maximum percentage error. Okay, so the idea is use nothing more than the tangent plane approximation. Okay, so what did you think? Hope you found this presentation useful. In upcoming presentations, I will be doing more live streams, more classes live. So if you have any questions, any suggestions, I always love to hear your comments. Thanks for watching. See you soon, everyone. Bye.